Okay. Thank you for the introduction. Good morning, everyone. My name is Sadik, and I'm a PhD student at Florida International University. And today I will present a paper titled Disassembling Software Instruction Types Through Impedance Side Channel Analysis. In this paper, we explored the potential of impedance as a side channel. So this is the outline I will be going over today. I will first introduce the traits and topics, then the existing solutions and their limitations. Following that, I will present our proposed methodology and their limitations, then the results of our experiment. So recent cyber attacks on embedded devices highlight the urgent need for protection against malware and preserving software privacy. These cyber attacks may originate from multiple sources, including the foreign countries, terrorists, hackers, and even global supply chain. And in addition to these attacks, counterfeit devices may allow malicious firmware or software into the system, and then the system firmware vulnerabilities can be exploited to install malware or steal sensitive data. And the consequence may result in functional modification, compromise of privacy, loss of control, and even damage to the system. By 2021, the global ransomware damage cost was around $20 billion US, and it is predicted that by 2031, the cost will exceed $265 billion US. So here are some attack methodologies. First, there's overwriting malware. It overwrites the target executable, and since it's overwriting the target executable, it's easier to detect. And there's another type of malware, that's prepending malware. It's a type of malware that adds malicious code to the beginning of a legitimate file without altering its functionality or size in order to evade detection by security software. Then there's appending malware. It adds malicious code to the end of legitimate file, also without altering its functionality or size. Then there's multi-cavity malware, is also known as multi-stage malware, is an advanced type of malware that uses multiple stages to achieve its objectives. And each stage is responsible for performing a specific function. And at the end, there's kernel rootkit. It's also a type of malware that can modify the core operating system to hide its presence and avoid detection by the security software. So there are some software-based solutions to prevent this type of attacks, like the anti-malware. It provides real-time solutions, and it prevents data loss and system downtime, but it has some limitation that it can be resource intensive and it can be bypassed. Then there's encryption-based solutions. It protects data access from unauthorized parties and helps to maintain the integrity. But incorrect implementation may cause vulnerabilities, and it may impact the performance of the system. So it's not a complete solution. And there's the hash checking option, which prevents unauthorized modification to the firmware or critical data. So it ensures the stored data is accurate and not corrupted, but it needs updated hash values, and it relies on trusted source, and malware and unauthorized access can still evade this system. So since the software-based solutions are not enough, we need some hardware assistance, and this is because the hardware is the bottom of the trust layer, and lower layer like firmware cannot be seen by the operating system layer. Therefore, the malware, the antivirus, which operate on the operating system layer, they cannot protect the firmware. This is why we need some hardware assistance to defend the system. And here's an example of a malware getting embedded into a program and treated as a BNN program. So if the software-based solutions misses to detect this kind of malicious program, it may cause harm to the system. And there are some hardware-based solutions also, like the hardware performance counter. It provides a low-level view of a system performance, so it can be used to detect attacks and prevent this kind of attacks. But it may introduce additional performance overhead into the system, and it's still possible to evade this type of system. And there's another hardware-based solution is the trusted platform module. It stores sensitive data from unauthorized access, so it verifies the integrity of the software and the hardware, and it also difficult to attack or compromise, but it has some limitations like it can have exploitable vulnerabilities, and it trusts and relies on the firmware, so that's an issue. So let's say that the software firmware may be protected in memory and then not may be available to disassemble. So that's the problem, but we have some side channels that leak system information via the physical characteristics. So we can use the side channel to monitor the system behavior and disassemble software instructions. And side channel analysis can indicate anomalies in a system. For example, a sudden increase in the power consumption or EM radiation may indicate an attack. And it may, the side channel analysis can also be used in disassembling software instruction in a system. In this method, we find the correlation of the side channel and the internal operations. So there are two popular side channels, the EM and power side channel analysis. EM measures the EM radiation of the devices, and power side channel measures the power consumption of a device. They have some limitations, like the EM side channel analysis may require sensitive equipment and near-field probes, and it may also require EMI-free environment. And the power side channel may require physical modification, like cutting the traces or desoldering the pins of the IC. Then it may have some calibration issue. And the major problem with power side channel analysis is that it provides an aggregated view of the net current inflow. So you don't see a specific response from a chip. You get the overall view of your device. So we used impedance as a side channel. So our hypothesis is that the impedance will change corresponding to the instruction is executing. So when the instruction A is getting executed, we will observe impedance Z1. When instruction B is getting executed, we will observe impedance Z2. And here's an example of a full adder circuit. Here the addition and subtraction are controlled by the mark selection bit. And the mark selection bit is changed, the corresponding corresponding devices and the data part changes. So we should observe two different type of impedance for these two type of operations. So in a paper, we formulated an analytical model for the CMOS inverter. The CMOS inverter has two states, and we show that the two states will change and depending on the operations, and we will observe two different kind of impedance for these two types of states. And in the NAND gate, we also observe that when the state changes, the corresponding impedance changes, and they are not identical. So we should see four different impedance for this NAND gate. And in our experimental setup, we used Arduino Uno as a platform, and we used vector network analyzer to collect the data. So vector network analyzer collects the S parameter of the devices, so we need to convert it to the impedance. So we did that in our experiment. And we used a coax cable to connect it to the PDN of the device. And we observed for 4 different cases, the impedance response are different in the highlighted regions. And we grouped the instruction types into 4 types, depending on the circuits they're using. So when the type 1 instruction is getting executed, it's using circuit 1, and when type 2 instructions are getting executed, it's using circuit 2, and so on. And this is the workflow of our work. So we first collected the S parameter measurements, then we converted it into the impedance signal. After that, we did the frequency selection. Here we first found the relevant frequency points, which explain the instruction types, and then we found the dominant frequency points that are accountable for the majority of the signal variations. Then we did the principal component analysis to reduce the dimensionality and complexity of the signals, and at the end, we used machine learning algorithms to classify the instruction types. So our VNA can collect 10,000 frequency points, and after the frequency selection, we found that 2,700 frequency point can adequately describe the instruction types. And we also observed the distribution of the response at those frequency points are defined, and then we did the principal component analysis and found that 1,200 features are enough to differentiate the instruction types. So we used machine learning algorithms like SVM, KNN, AdaBoost, and linear discriminant analysis, and we calculate the F1 recall accuracy. And we found that SVM with the cubic kernel that operates best, and we can achieve 98.6% accuracy with this model. And we also observed low false positive rate, like 0.4%. And from this work, we found that the impedance has the potential to be a side channel to disassemble software instruction types. So in summary, we demonstrated the use of impedance side channel analysis for disassembling software instruction types, and we observed low false positive rate and high accuracy rate. And in a paper, we also describe how impedance has the potential in anomaly monitoring, software integrity verification, and virus detection, and even detecting counterfeit components. And this can be an effective solution for resource-constrained embedded devices against cyber attacks. So in a paper, we actually explored the potential of impedance rather than comparing it to the power and EM side channel. So this is an early phase of the work, and we hope to work on this and try to find more interesting results in a future work. So this is it. Thank you everyone for listening, and I welcome questions.
Any questions from the audience?
Maybe I'm just misunderstanding, but the vector analyzer, I assume, takes some time to sweep the frequency and come up with your data, but the instructions execute in just nanoseconds. So how do you bridge that gap?
That's an excellent question. Thank you. So yeah, that's right. The vector network analyzer takes some time. So we didn't propose this solution for runtime attacks. So it's like you disassemble the instructions earlier phase before implementing in your system, and the vector network analysis actually takes takes some time. So we reduce our clock cycle in our device to disassemble the instructions. So the idea is to disassemble the instruction in an early stage, and currently we are still working to find a solution to implement in the runtime system. Thank you. I hope this answers your question.
Any other? No? Let's thank our speaker again. Okay, so our second paper is this one, okay. Bits to BNNs, Reconstructing FPGA, Machine Learning IP with Joint, Bitstream, and Side Channel Analysis. So the speaker, Brooks, he is now a PhD candidate at the University of South Florida. His research is in the areas of hardware security, reconfigurable computing, and adversarial machine learning. He's graduating this May. Congratulations. And will join the MIT Lincoln Lab this fall as a hardware security researcher. So let's welcome our speaker.
Thank you very much for that. Hi everybody. My name is Brooks. I'm really excited to be here to talk about some of the research that I've done with my advisor, Karam, in the past year towards reverse engineering neural networks directly from the FPGA bitstream. So first I'm just going to give some high-level info about what to take away from this talk. So theft of machine learning ML models poses significant risks of IP security because of the time and resources it takes for a company to develop a state-of-the-art model for a given application. The intellectual property has a lot of value, so it's important to protect those against theft. In general, FPGAs are a popular platform for edge applications that use machine learning platforms, and many approaches of model theft attacks utilize side-channel analysis-based approaches to derive secrets from these FPGA-based systems, so the secrets being the neural network weights and architecture parameters, that sort of thing. And at this time, no prior works consider the implications of FPGA bitstream reverse engineering in this context. All of the current work has been focusing on side-channel leakages. So in this work, we demonstrate that a significant amount of information can be derived purely from the bitstream, and that this information can help guide the side-channel analysis process. So for deploying neural networks to FPGAs, binarized neural networks, or BNNs, are a popular approach because they enable considerable memory savings for storage of these parameters in the block RAMs of the FPGA to quantize the weights and activations down to a single bit. And there's a lot of different toolkits for enabling this technology, and one of the important ones that I want to focus on is Xilinx's Fin toolkit, which is a data flow compiler for generating high-level synthesis, or HLS, code for implementing BNNs on FPGAs. And essentially it involves folding the computation of these BNNs over a number of processing elements, or PEs, with a number of SIMD data samples fed to each PE on every clock cycle for computation. And there's been a lot of different approaches to performing model extraction attacks on these types of networks in FPGA. And largely they can be differentiated based on what type of assets they're able to recover. So some recover just the architecture, the weights, both, and typically it involves a process of simple power analysis or visual inspection to derive architectural features of the network, and then a higher level differential or correlational power analysis to be able to recover the actual weights and parameters during computation. Some other recent approaches look at training different models on the raw power traces to classify certain architectural features of the models. And Myers et al. In a recent work actually demonstrated a successful attack on the Fin framework where they were able to recover different folding configuration parameters, which is it's an interesting complementary result to what we present in this paper. So just to give some high-level overview about the Xilinx 7 series FPGA bitstream, it consists of 32-bit words of data with 101 words making up what's called a configuration frame. And the configuration process consists of a series of reads and writes to configuration registers. And in particular, the frame address register points to which element a frame goes to. And that frame address register stores information such as what configuration block interface is being configured, and what location the particular tiles are in the FPGA, so row, column, and top or bottom of the FPGA, that sort of thing. And the frame address register is typically initialized to 0 and then auto-incremented as frames are shifted into the device. And what we see is that the configuration data for logic blocks and interconnects and stuff occurs first in the bitstream, and then towards the end of the bitstream we see all of the block RAM initialization contents. So reverse engineering of this FPGA bitstream format is useful for a number of different reasons. For example, creation of open source toolkits, or as the precursor to various different types of attack. We've seen this a lot in the research community. Jonathan Graf's presentation earlier covered a lot on this topic too. It can be useful for aiding in the design process for like partial reconfiguration, for malicious purposes like inserting hardware trojans, and one thing I want to emphasize is the open source community. So The project, the F4 PGA effort, is a large-scale effort towards creating an open-source toolchain for FPGAs, and it leverages other efforts like Project X-Ray to understand the format of the bitstream for different devices to be able to target them. So now that we have some understanding of binarized neural networks implementation on FPGA and bitstream format, I'm going to spend the rest of the talk talking about how we take this reverse engineering information and recover certain aspects of the binarized neural networks directly from it. So the goals of this project were to demonstrate the dangers of bitstream reverse engineering in the context of model theft of machine learning models. And we wanted to, in particular, attack a popular HLS-based ML deployment tool, the Xilinx Fin framework that I talked about earlier. And at this point, no one has even hinted towards the possibility of this in the literature. People may say that the bitstream can be reverse engineered and maliciously modified, but there is an inherent difficulty to doing that with complex machine learning models that have parameters stored in the different block RAMs. So hopefully the work in this paper kind of helps illuminate some of the difficulties that might be inherent of that kind of effort. So essentially the bitstream parsing portion of the attack involves taking an unencrypted copy of the bitstream and extracting the configuration frame data. Then we use a open source FPGA bitstream database that tells us what the frame layout is of all of the different configuration frames, the particular bits in those frames that enable or disable certain components, and then the connection points between different tiles in the FPGA where they're connected. And this information is important mainly for reverse engineering the contents and configuration of block RAMs and interconnects. And then finally, once we have the configuration of all of the memories, we can inspect the interconnectivity between these different block RAMs to form groups. And essentially, these different groups of block RAMs correspond to the weights that make up a particular layer. So for instance, in this example, 4 of the block RAMs are all connected to each other and isolated from the rest, and those might correspond to the first layer in the neural network, and 3 for the second, and so on. So to use Project X-Ray for this, there's 3 important files that we that help us do this. So first is the part.json file, and essentially that tells us for every region of the FPGA row column how many configuration frames belong to that area of the FPGA. And so this informs the distribution of the frames throughout the rows and columns and the different configuration buses, and allows us to reorganize that frame data from the unencrypted configuration data into a multi-dimensional array that we can then index using the different values that make up the frame address register. And then in the tilegrid.json file, which is the file on the right-hand side, that for every cell in a particular FPGA part, that tells us the base address, so essentially where its frames are located in that multi-dimensional array, and then it tells us how many words from that slice of the configuration data go to that particular component. And then finally, the segbits file tells us which particular bits in those words have to be set or unset to enable disable a certain configuration element. So this example here of the segbits file shows which bits need to be configured in a particular manner to set the read width for a given block RAM. So once we've gone through this process and reversed the contents and configuration of every block RAM, we have to actually go from this abstract representation from the bitstream, from the block RAM makeup to what the actual array is that's stored in the BRAM. So Xilinx BRAMs have 36 kilobit primitives that are comprised of 2 18 kilobit primitives, and the initializations for them are spread across the init or initialization and then the parity vectors, parity for error correcting codes. But when you're not using ECC, the parity vectors are used to actually store memory contents. And so to go from the abstract, init p vectors, which are like 64 or 128 by 256 bit vectors, we take the contents from the 2 18 kilobit memories and interleave them, and then concatenate the parity vectors to the right-hand side of the initialization vectors. And so at that point, we can reshape the data so that we have rows of 256 and then plus 32 bits of parity data. And at that point, when you have initialized the contents of the blockgram, you might not fully utilize it, so there are zeroized rows in the configuration, the initialization data. So we prune the 0 rows and then reshape to the given read width for that blockgram, and then there can be zeroized columns as well for if the read width is over allocated for that given RAM. So at that point, we have the reduced array that is actually stored in the blockrams, and let's say it's like an n by m array. And once we've performed this for all of the blockrams and we have grouped them all together, if you read the data from the groups row by row, like 0, 1, 2, 3, the data that's actually stored in them starts at like the top left-hand corner of the weight matrix for a neural network layer, and then traverses down and all the way until it gets to the bottom right-hand corner. And that the amount of data that's stored in there and how much is in each row is determined by the folding parameters from Fin. So for grouping the actual blockrams together, we do this by generating a map of interconnect tiles using tickle commands in Vivado, basically to know from one interconnect and one port on that interconnect what other tiles does that feed to. And then we look at the pseudo-programmable interconnect points, or PPIPs for Project X-Ray, to know which particular ports are hardwired into a particular location. And this tells us that the output clock register enable pin is located in a particular spot. And what we do to group the blockrams is we start from a list of all of the allocated blockrams, and we pick one and then perform DFS, a depth first search from that blockram, and then add all of the blockrams that are visited to a group. And then once that terminates, we start it over with the other blockrams that are allocated. And then once it terminates, it will return a list of all of the different groupings. So this doesn't tell us everything, though. So from the bitstream, we know how many groups or layers there are, which blockrams correspond to each layer, and what the total read width and depth is of each layer, and so the size of each layer. Through side channel analysis, we need to determine which group is which layer through simple power analysis, and then the order of the BRAMs in a group through differential power analysis. And for gathering the trace data, we used a Chip Whisperer 305 board that has an Arctic 7 FPGA. And we take the circuitry, the Verilog files generated by Fin, and add some additional files to synchronize the data loading and trace capture. So for the simple power analysis, it works well for fully connected networks because there's no overlap in the layer execution, but not as well for the convolutional neural networks because there is overlap from the ones we tested. And for differential power analysis, once we know which layer corresponds to which BRAM group, we can set up a template function to determine that ordering. And that template function is the binary multiply accumulate between the weights and the input. And so we compute the template as a partial Hamming weight for each process element, and essentially use that to guess which is the 0th BRAM. And then once we have the correct guess for that, we guess the first, and so on and so forth. So we evaluated using two different networks that were generated by Fin, a fully connected and a convolutional. Both of them are quantized to single bit activations and weights. And so for the evaluation, we want to look at the fidelity of the model. Are the hyperparameters correct? Do we have the correct number of layers, sizes of layers? And how close are the parameters, like the weights in each layer? And so the attack itself was successful. It was able to get the hyperparameters correct, so the sizes of layers and how many there are just from the bitstream, which is shown in the two tables for each network. And the side channel analysis approach helps us determine which layer is which, but more work needs to be done to determine the correct ordering for the blockrams. The differential power analysis approach was able to was not able to derive the correct answer every time, but still narrowed down like a 32 factorial search space down to a much smaller number. For example, like if there's a layer with 32 BRAMs. So now I'll just quickly wrap up. So in this work, We presented a method of leveraging open source FPGA device databases, Project X-Ray, to reverse engineer the BRAM contents directly from the Bitstream and infer their connectivity. We achieved partial reconstruction of the neural network models in the FPGAs using Bitstream and side channel analysis, and we targeted a popular framework for deploying BNNs to FPGAs. The more work needs to be done, but this is a step in the right direction, and I think that if we're able to demonstrate full reversal purely from the Bitstream, this can enable other efforts such as neural network Trojan insertion, like flipping some bits of weights in the neural network to achieve a hardware Trojan. And if you're interested in this work, please reach out to myself or my advisor, Robert Karam at USF. And at this point, this concludes my talk. Thank you to the organizers, session chairs, and NSF, and everybody. I'm happy to take your questions.
Sandia National Labs. So it seems to me that once you have the Bitstream, you could also simulate the gates and come up with some of the same information you were obtaining through side channel analysis?
Yeah, I suppose you could do that. At that point, we have the RTL already because we implemented the model using Fin. So we used that some to understand how Fin's computation worked, like how it loads data and stuff. So that helped us set up the template function and whatnot. But yeah, I guess that would be one way to infer some of that information rather than through side channel analysis.
You probably don't have all the tools that you need for doing that.
No, not necessarily. Essentially all I was working with was Vivado and the Tickle interface to get some more information from interconnectivity, and the Project X-Ray database is a very impressive effort towards documenting the Bitstream. I'm not sure why it's allowed to exist, but it's
because it's invisible.
Yeah,
it's X-ray.
Yeah, right. But so the information that's in that open source project was really useful in enabling this effort. But yeah.
Okay, thank you.
Thank you for your question.
Sorry about this open FPGA database project that you talked about. I think you guys do not have the do not have access to the proprietary format of the Xilinx, yes? Then how did you guys do the mapping from your database to the format that the FPGA could be programmed to?
So what I didn't test is manipulating the Bitstream in any way and then actually testing it on the FPGA. But the Project X-Ray database has like a very sophisticated set of like fuzzers and stuff to determine which particular bits correspond to a different tile. And so the files that we used to understand that information, like I have those in my slides, but yeah, they have information about timing of different paths as well. And so all of that information is leveraged by this F4PGA toolkit, which was formerly SymbiFlow, if you've heard of it. And they use all of that information from Project X-Ray to generate bit streams for 7 series devices. So I'm not affiliated with Project X-Ray at all, but that's essentially how I understand that they were able to construct the frame mapping between, or the mapping between different bits in the bit stream and what particular components it sets to different
Can I ask a
configurations.
question? And if you want to do the same thing with another FPGA vendor like Int'l, maybe Atmel or others, can you still do that?
Yeah, so so Project X-Ray is for Xilinx 7 series devices, but in this figure here actually is a figure from the F4PGA project, and they have the Project Ice Storm, which documents the format for Lattice FPGAs, and then I forget which one Trellis is, but they also have microarray for the UltraScale Plus boards. So they have several things that I've heard of, but they don't have any Altera, Int'l, FPGA documentation. So I'd be interested to see how a tool like Fin obviously is made for Xilinx FPGAs, it's by Xilinx, but how a similar tool might leverage resources for an Int'l FPGA. I think that the methodology here that I've presented is transferable, but the resources available for Bitstream documentation are relatively limited. So that would be a limiting factor. You would have to first do something crazy and potentially illegal to understand the format for a different device.
Okay, thanks so much.
Yeah, thank you for your questions.
All right, maybe let's thank our speaker. All right, okay, so let's come to the third paper. Third one is the LEDA, okay, locking enabled differential analysis of cryptographic circuits. So the presenter, Devanshi, she's now a PhD student at the University of Stuttgart. She's working on secure composability of cryptographic hardware and also including other researchers' interests such as hardware and network security. So how about let's welcome our speaker.
Thank you so much for the introduction. Hi everyone, welcome to my talk on LEDA, locking-enabled differential analysis of cryptographic circuits. Here is the outline of my talk. I will start with some simple background and motivation behind the work, then I will introduce our attacks and show the results of our different experiments. I will then discuss the analysis of our successful attacks, and finally I will conclude my talk. So the demand for security and privacy of sensitive data that travels between different devices has been increasingly becoming more and more important, and our cryptographic primitives provide just that, exactly that. While on the other hand, as we have seen quite extensively in the last couple of days, the decentralization of IC design has led to many more opportunities for different threat vectors. And this has led to a lot more hardware security vulnerabilities like IP piracy, counterfeiting, reverse engineering. And our design for trust solutions like watermarking, camouflaging, and logic locking were introduced to protect against these hardware security vulnerabilities. So for the purpose of this work, we focus specifically on logic locking. The hardware implementations of our cryptographic circuits need to be protected against all different kinds of threats. They need to be protected against physical attacks like fault injections, side channel analysis. They also need to be protected against supply chain threats like hardware trojans, overbuilding, etc., which raises the question of secure composability of our countermeasures. That is, whether protecting our circuits against one kind of attack is making them more vulnerable against maybe another kind of attack. In this work, we studied the consequences of applying logic locking to cryptographic hardware, and we introduced two types of attacks, locking-enabled differential analysis, LEDA, and locking-enabled differential fault analysis, LEDFA, which is basically just fault-assisted LEDA. For this purpose, we considered two broad families of logic locking schemes, pre-SAT and post-SAT logic locking for people who are not familiar with them. On the left-hand side, you see a simple example of random logic locking using XOR and XNOR insertions, such that the circuits shown in figures A and B would be equivalent, functionally equivalent, if and only if the correct logic locking key, LK, is applied to the circuit. We consider two variants of this scheme using random AND and OR insertions and using random XOR and XNOR insertions. On the right-hand side in figure A, you see an example of a generic point function-based logic locking scheme. And these schemes introduce a single point of perturbation or error into the circuit functionality based on this point function y, which again is dependent on whether or not the correct logic locking key is applied. Again, we consider two types of such schemes. In figure B, you can see anti-sat logic locking, and in figure C, you can see stripped functionality-based logic locking. So here is our overall attack methodology. What we do is we take a hardware implementation of a cryptographic primitive. The different ciphers that we have considered for this work are LED present, which are both lightweight ciphers, and we also consider a small scale variant of AES and the AES. The secret cryptographic key K, which is shown in red in this figure, is the target of the attack, not to be confused with the logic locking key LK. So we want to extract or retrieve the secret cryptographic key, and we are not trying to attack the logic locking schemes. So we take this cryptographic circuit, or the hardware implementation of the cryptographic primitive, and we unroll it into a one-cycle implementation using time frame expansion. And this time frame expanded circuit is then logged using NEOS, which is an open source netlist encryption and obfuscation suite, based on the different locking parameters that you would want and you can choose. Once we have this logged cryptographic circuit, an attack formula is constructed using our algebraic fault attack framework called AutoFault. In order to construct this formula, what we do is for LEDFA, we unlock the logged cryptographic circuit using a randomly generated incorrect logic locking key. And we use this incorrectly unlocked cipher to do our encryptions. And we then perform a differential analysis on these different encryptions in the presence of faults and the absence of faults. So for LEDA, there are no fault injections. We simply perform differential analysis on multiple circuits that have been unlocked using different randomly generated incorrect logic locking keys. This attack formula is then converted into its conjunctive normal form using Gaussian transform and is fed to a SAT solver to extract the secret key or to solve this attack formula for the secret cryptographic key. Here are the average solve times for our LEDFA results. The first row in green shows the results for differential fault analysis for comparison when no logic locking is applied. And we can see that the complexity of LEDFA is significantly lower compared to differential fault analysis. For example, if we look at the table, we can see that we need around 1,300 seconds for differential fault analysis to attack an implementation of present with 5 fault injections, while it takes only around 6 seconds for LEDFA if random logic locking using 128 and an OR insertions is applied. Yeah. Similarly, differential fault analysis on AES using 2 fault injections takes around 15,000 seconds, while LEDFA takes only around 2,500 seconds if the circuit is locked using a 64-bit anti-SAT logic locking key. For LEDA, we see that the logic locking can make our cryptographic circuits vulnerable to classical algebraic analysis. Like I said earlier, there are no fault injections applied here. We use multiple randomly generated logic locking keys, incorrect logic locking keys, to unlock the circuit and apply differential analysis to solve for the secret cryptographic key. And here, in this case, we observed an average 50% success rate for both variants of the random logic locking schemes. which is interestingly much lower than the average 70% success rate that we observe for anti-SAT, even though random logic locking is such a primitive scheme. However, our attacks did not succeed on circuits locked using stripped functionality logic locking, and we were also unable to successfully recover the secret cryptographic key for a full-scale AES implementation. The successful result you see here are for the small-scale AES implementation. So why do these LEDA attacks work at all? And why do they work better for anti-SAT compared to a primitive scheme like random logic locking? So in case of random logic locking schemes, as the name suggests, locking key gates are inserted randomly at multiple locations in the circuit. And one such incorrect locking key bit, let's call it LK prime, would have the same effect as a single bit flip fault in the circuit. Yeah? And the presence of these gates at desirable locations in our circuit would make our attack formula much simpler and easier to solve than it actually should be. On the other hand, two such simultaneous bit flips could cancel out the effects of each other. So as you can see here, an error generated due to an incorrect locking key bit LK0 prime at the input of an S box can later be canceled out by another error that is generated using, because of another incorrect locking key bit, LK1 prime. Yeah. But this effect of canceling out can explain the lower success rate that we observed for LEDA attacks using random logic locking. Here we demonstrate an attack with hand-picked incorrect logic locking schemes to see what exactly happens. We analyzed an implementation of LED, which is locked using an 80-bit random logic locking key, and observed that there are specific locking key gates. There were specific locking key gates corresponding to LK11, 24, 27, 47, and 62, affecting the operation of round 29 of LED, which is a desirable location for differential fault analysis on LED. And we constructed an attack formula with incorrect locking keys that differ from the correct logic locking key, which is shown in the first row of the table here, at these specific key bits. And in this case, we had a success rate of 100% compared to the 26% success rate that we had with randomly generated incorrect logic locking keys. On the other hand, point function-based logic locking schemes insert only one source of perturbation towards the end of the operation of our circuit, which eliminates this possible interference of the effects of different incorrect locking key bits. Yeah. But what these schemes do is they insert a logic locking block, a separate logic locking block into the circuit, which has two inputs. One is the logic locking key, and the other is a tree input set represented by X here. And what this tree input set is a subset of the primary inputs of the circuit for anti-SAT, which is not good, and a subset of the primary inputs and some intermediate wires for stripped functionality logic locking, which we will see is a little bit better. So this creates basically new propagation paths between the cryptographic key and the circuit outputs through the logic locking block, which is not only cryptographically insecure, but also much smaller compared to the rest of our circuit. So for example, LED has a size of around 67,000 gates, while a 64-bit anti-SAT logic locking would only add 67 gates to the circuit. So in order to see the influence of this tree input set, we picked specifically locked circuits with different number of cryptographic key bits in the tree input set for the logic locking block, and observed that the circuits become more vulnerable and easier to solve, to attack, with a larger number of cryptographic key bits in this tree input set. We can see here for present that is locked using a 128-bit anti-SAT logic locking scheme. We need 105 seconds, only 105 seconds to recover the cryptographic key when 51 bits of this cryptographic key are a part of the tree input set. compared to the 1800 seconds approximately needed if only 24 bits are a part of the tree input set. Similarly, for full-scale AES that is logged using a 128-bit stripped functionality logic locking, we are able to successfully extract the cryptographic key in 10,427 seconds approximately if 65 bits are a part of the tree input set. Important thing to note here is that we initially had a success rate of 0% for LEDA with, on circuits that are logged using stripped functionality logic locking, and we were unable to attack a full-scale AES with our random attacks as well. But here we can see that it is possible to attack both the full-scale AES and also the circuits that have been logged using stripped functionality logic locking. So to conclude, the incorrectly unlocked circuits implement functions with reduced cryptographic strength, and our attacks were effective even with randomly generated logic locking keys, but optimized attacks led to a significant improvement in our success rate. So this work shows that it is not safe to use methods like logic locking on cryptographic circuits. And even though logic locking schemes were not introduced or developed specifically for cryptographic circuits, there is no existing work that explicitly excludes them. A part of a cryptographic circuit could be a part of a larger IP core that the designer might want to protect using schemes like logic locking. Therefore, the designers must stay clear of adding locking key gates at critical locations in the cryptographic circuits, and especially prevent cryptographic key bits from being fed directly into the locking subcircuits. Future logic locking schemes could also be extended to detect recurring applications of an incorrect logic locking key, similar to the detection of fault injections or tampering attempts. But yeah, finally, I would like to say that we can't look at our different threat models or our different attack vectors in a vacuum from each other, and we have to look at the interactions of our different countermeasures and look at a secure composition of our overall countermeasures. Thank you.
Yes, any questions?
Kaveh Shamsi, UT Dallas. Thank you for your great presentation. So my question was that in the threat model, you assume that the keys are fed by flip-flops that can be flipped using faults?
Yeah.
So if there are some logic locking circuit level implementations that don't use those. So for instance, you take an anti-fuse and burn it and then just tie the key bit to high.
Yeah.
And that would sort of thwart something like this, right?
Definitely, definitely. There are also already schemes like, for example, the strip functionality logic locking flexibility type that already lets the designer sort of decide what part of the logic to protect or what logic codes to protect, choose the protected input patterns basically. That would already be a better solution, and we would not see so many successful attacks here. Yeah. Similar to, again, I think the cyclic logic locking, which is, I think, from your group or from you.
Yeah, it depends on how you implement it. If you do it with anti-fuse, then.
Exactly, which would also create something similar, would have like loops in the circuit, which may or may not be ideal for cryptographic circuits, but again, such attacks would not be possible.
Thank you very much.
Thank you.
I think in the conclusion you mentioned that if you use logic locking, it can weaken the strength of the crypto components, I guess.
Yeah.
And what if you use the logic locking as a separate layer and around the crypto block?
Yeah, like I said, it could be a part of a larger IP core that is being protected, right? So I would say it would be ideal to exclude the cryptographic parts or the cryptographic hardware and just lock the rest of the hardware if it is essential. But in my opinion, locking the cryptographic hardware in itself doesn't help. It makes it more vulnerable, makes the hardware implementation more vulnerable. Of course, the cipher in itself is still secure.
No, my point is, if What if you instantiate your crypto block inside the wrapper, and in the wrapper you use logic locking?
That is an interesting point. Definitely, I do think that would be interesting to look into.
Okay, thanks.
Thank you.
Hi, a naive question probably. So you're leveraging the logic locking components to improve your controllability over the cryptographic engine to allow you to brute force the key? Is that what I am to glean from this?
Not really brute force the key. We're doing differential analysis. So, like I said, we incorrectly unlock the circuit, and now we have an encryption that is an encryption function that is not the same as the real cryptographic function.
Correct. Right.
And then we perform differential analysis on this incorrectly unlocked function. So we do one encryption, a fault-free encryption, another faulty encryption, or multiple faulty encryptions, and then do a differential analysis of that.
Interesting. Yeah, so your goal is to find the cryptographic key, not the
Not the
unlocking
locking key.
So you know what the unlocking key is, you know what the
Yeah.
I see.
Yeah.
Okay.